Problem 42 is a little change of pace from some of the other things we did. Initially, when you look at the problem, you're thinking, oh, this is another Pythagorean theorem problem, but it's actually not. It actually involves a little bit of trig. So we have a balloon. Here's our balloon that's rising up into the air. And we have an observer that's standing 50 meters away from the spot right below the balloon. Okay, that's a constant value, so we're going to plug it into the problem early on. The observer doesn't move. But as the balloon rises, the angle of elevation, which I defined as theta, is going to change. Okay, and we're wondering, what is that rate of change of theta when the balloon is at 50 meters? So what's our general equation? Well, our general equation here becomes the trig value that we would get from this right triangle trig. So the tangent of theta is equal to y over 50. And again, I can put the 50 in right away because the observer on the ground never moves. So that distance is constant, so that goes in right away. Now, for some of you, you might see this and want to dive into this as a quotient rule. And I can't stress enough how much easier it would be if you recognize this as being 1/50th times y. Okay. Can you do that as a quotient rule? Yes. Is it the quickest way to do it? Probably not. Okay. We know that the balloon is rising at a rate of 4 meters per second. Since the balloon is going up, then that's a positive value because the value for y is getting bigger. And we want to know what the, like I said, we want to know what the rate of change of the angle is when y is equal to 50. So, general equation, taking the derivative there, we get secant squared theta, d theta dt, and yes, you need a d theta dt. Anytime you take the derivative of a variable with respect to time, you've got to stick the d whatever over dt on the end of this. And again, the reason I simplified this is because we get 1/50th dy dt as the derivative. Now, if you did the quotient rule, would you get the same answer? Yes. It would just take a little bit of simplifying to get to that point. Okay, what do we know? Well, we know what dy dt is. We're looking for d theta dt. What I don't know is what is theta. Okay, so I have to do a sidebar here, as we commonly do in these problems. So I want to know what is theta when y is equal to 50. Okay. So you don't have to be a genius to recognize that we're going to do the tangent of theta is equal to 1. Well, what's theta when tangent equals 1? Theta turns out to be pi over 4. And yeah, we're working in radians here. Could you do it in degrees? Yes, but I prefer radians. Okay, I think we're good to go. Now we can plug and chug. What I would do to make my life easier, and I think many of you would agree with me, is that most people are better working with sines and cosines versus secants, cosecants, cotangents, and tangents. So I'm going to solve for d theta dt before I plug and chug. And the reason I do that is because the secant squared is 1 over the cosine squared. Therefore, if I move it to the other side of the equation, it just simply becomes cosine squared theta. I still have a 1/50th there, and I still have a dy dt. Okay? And I would argue that that's an easier way to solve the problem instead of having to figure out what the secant is, which is something that most people aren't very strong at. Okay, so now we can plug and chug. D theta dt is equal to 1/50th times the cosine squared of pi over 4 times 4. You could use your calculator. You could use your vast stores of trigonometric information or knowledge to figure out what the cosine of pi over 4 is. It is on the unit circle, so it's doable. If it's not on the unit circle, then you rely on your calculator. But after solving all this, we find that d theta dt is equal to 1/25th radians per second. Now, does that answer make sense? Well, I don't know. But the one thing I do know is that as the balloon goes up, the angle's going to get bigger. And so I got a positive answer, so that makes me feel good. That's a common situation here where you don't know numerically if it makes sense, but just looking simply at the sign will be a helpful indicator as to whether or not you got the problem correct.